Have you ever just looked up at a stormy sky and bam, you see a flash of lightning? It is absolutely one of nature's most incredible and, let's be honest, intimidating shows. But behind that brilliant flash, there's this amazing story of physics and electromagnetism. So, let's get right into it and break down exactly what's going on up there.
So, the million-dollar question, how is lightning even made? How does the sky create a spark that is so huge, so powerful, that it can connect all the way to the ground? Well, it's not just one single thing that happens. It's actually a step-by-step process that starts completely invisibly way up inside the clouds.
Okay, so our story starts inside a big old storm cloud. And inside, there's this chaotic, totally invisible battle going on between tiny particles. This is the engine, the powerhouse, that gets the whole lightning strike started.
So inside these massive, swirling clouds, you've got these powerful currents of air shooting up and down, updrafts and downdrafts. And as tiny little ice crystals and water droplets get tossed around in there, they're constantly bumping into each other, rubbing against each other, creating all this friction. This process literally strips electrons away, and that separates the electrical charges. What happens next is kind of like sorting laundry. The lighter, positively charged particles get carried all the way to the top of the cloud. Meanwhile, the heavier, negatively charged particles sink down to the bottom. This is the first absolutely critical step. It turns that storm cloud into a giant separated battery just hanging out in the sky.
All right, so now the cloud is all charged up, and it starts to have a pretty big effect on the world below it. This invisible tension starts to build and build between the sky and the ground. That huge collection of negative charges down at the bottom of the cloud, well, it starts to act like a super powerful magnet. It pushes away the negative charges on the surface of the Earth and pulls the positive charges up towards it. This whole process is called electrostatic induction, and it basically means the patch of ground right under the storm cloud becomes positively charged.
So now you have this separation of charge, negative in the cloud, positive on the ground. And that creates this incredibly powerful, invisible electric field between them. Just think of it as the zone where all that electrical force is active. This field, this is the fundamental driver of the entire lightning event. It's the force that's about to tear right through the air.
And the amount of potential energy stored in this field is just staggering. I mean, we're talking about a voltage difference between that cloud and the ground that can hit hundreds of millions of volts. Seriously. Imagine the pressure building up behind a gigantic dam. That's the kind of energy we're dealing with here, just waiting for a chance to break free. All right, the stage is totally set. We've got this massive electrical potential just ready to be unleashed, but there's one major thing standing in the way, and that's the air itself. Let's see how that tension finally hits its breaking point.
Under normal conditions, air is an excellent electrical insulator. Thank goodness, right? If it wasn't, we'd have electricity arcing between everything all the time. And it's this insulating property that's holding back that enormous voltage in the cloud. But it can't hold on forever.
When that electric field becomes just overwhelmingly strong, it literally rips the electrons right off the air molecules. This moment is called dielectric breakdown. The air, which was just an insulator a second ago, becomes ionized. It turns into a conductor, basically a plasma channel that's ready for electricity to flow right through it.
Now, this path to the ground doesn't just appear all at once. Instead, it gets created by two separate channels of plasma that are basically racing toward each other in this spectacular midair connection.
And what's so cool here is that this connection happens from two different directions at the same time. Coming down from the cloud, you get a channel of negative charge called a stepped leader. It kind of snakes its way down towards the ground in these jagged little steps. At the same time, that super strong electric field is pulling positive charges up from the ground, or anything tall on it like a tree or a building. And this forms an upward-reaching channel called a streamer. So it's a race to connect. And when that downward-moving stepped leader finally meets an upward-reaching streamer, bam! The circuit is complete. A conductive superhighway has just been built between the cloud and the ground, and that connection is the trigger for the main event.
And here we go. This is the moment we've been building up to. The spectacular, brilliant flash of light that we actually see and call lightning.
The instant that path connects, it's like opening the floodgates of that massive dam we talked about. All that pent-up electrical energy is finally unleashed in one go.
And it happens unbelievably fast. But here's the part that might blow your mind. The initial path down, that stepped leader, it's actually pretty faint. The brilliant flash we see is called the return stroke, and it actually travels up the channel in just tens of microseconds. That's millions of a second.
So as this huge return current surges upward from the ground back to the cloud, it superheats the air in that channel to temperatures hotter than the surface of the sun. It's this intense heat that causes the air to glow so brightly, creating the flash we see, and it also causes the air to expand explosively, creating a shockwave that we hear as that mighty roar of thunder. So that bright bolt you see, it's actually racing up from the ground, not down from the sky. Wild, right?
So when you boil it all down, what's the core science that makes this incredible thing possible? It really comes down to three key concepts that work together.
First, you've got the electric field. That's the underlying force, the reason any of this happens. Then there's voltage. You can think of that as the potential energy, the pressure in the system that's fueling the strike. And finally, you have the current. That's the actual flow of charge, the thing we actually perceive as that brilliant, hot, powerful flash of lightning.
And that, in a flash, is the science of a lightning strike. But it does leave us with one final classic question to think about. If the light and the sound are created at the exact same moment, why do we always see the lightning before we hear the thunder? Something to chew on next time you're watching a storm roll in.